A rational equation is an equation containing one or more rational expressions, often with a variable in a denominator. And so if you look at the examples here, in this lesson we'll explore how to solve each one of these rational equations. There are 4 basic steps to solving a rational equation. Step 1, you want to list any restrictions that exist. Step 2, you clear the equation of fractions. Step 3, you solve that resulting equation. And step 4, you check the possible solutions in the original equation. Before we perform these 4 steps, let's just clarify 2 things. First of all, what a restriction is. We remember from lesson 1 of this unit that a restriction is any value that makes the denominator equal to 0. So we do not want zeros in our denominator, and if that is the case, then we call that a restriction. So we want to, first of all, identify what those restrictions are. And then the second idea is the idea of clearing fractions. And to do this, clearing fractions, you must multiply both sides of the equation by the least common multiple of whatever those denominators are, the least common denominators. So let's look at these 3 examples and perform these 4 steps to solve these rational equations. Our first rational equation, 2 over 3x plus 1 over x equals 10. The first thing we want to do is list any restrictions. We look at our denominators and we have x in both of our denominators. And if we look at both of these denominators, if you had plugged a 0 in for x, that would make those denominators equal to 0. So that means that 0 is a restriction. So 0 cannot be one of our solutions. Let's go in and solve this equation now. The next step we want to do is clear the fractions. So we're going to multiply both sides of the equation by our least common multiple. In this case, our least common multiple would be 3x. 3x will clear all of our fractions. So we distribute that. Here in our first equation, the 3x's cancel. That leaves us with just 2. Remember to divide by the numerator first and then multiply by the numerator. So we divide by the denominator. 3x times x cancels out our x's, which leaves us with 3. 3 times 1 is 3. And 3x times 10 gives us 30x. Now we're on to step 3. We just want to solve this linear equation. We combine like terms, isolate the variable, simplify our expression. So our solution, it appears, is 1/6. Before we mark that down, we want to go back and check to make sure that that was not restricted. We see that our restriction was 0, which means that 1/6 can indeed be our solution. And so we put that in our solution set, and we've solved our first rational equation. Let's look at the next example. Let's follow those same 4 steps. Let's begin by listing our restrictions. Here we notice that our denominator is a plus 7, actually for both of our rational expressions within the equation. So we know that for both of these denominators, a cannot equal -7. Because if you plug a -7 into either denominator, you'd end up with 0 as a denominator. So that would make it undefined. So we know that -7 is restricted. We'll want to pay attention to that later on in the equation. So let's solve this. To do that, we want to clear the fraction. In this case, a plus 7 is the least common multiple. That is what's going to clear our fraction. So this actually is a pretty easy step since it just cancels out. A plus 7 cancels with a plus 7 to give us 3. Here, a plus 7, again, cancels with our denominator, so we're left with a plus 10, the numerator. Now let's just solve this equation. Subtract 10 from each side. And we get a equals -7. So -7 is our possible solution. Before we circle that, let's go to make sure that that wasn't restricted. And as we go back and check what our restrictions are, we actually found that -7 was a restricted value. So before we started this equation, solving it, we already identified that -7 cannot be a solution. So even though we got -7 as a possible solution, we now need to cancel that out and recognize that -7 is not a solution, and there are no other possibilities. So that means that for this rational expression, there's no solution. There's no value that would solve this, because the one possible value that we did get was actually restricted. That's why it's so important to check those restrictions. Let's do one more example together. In this one, we want to identify our restrictions. So our restriction, x cannot equal the value 5, because if you plug a 5 into this denominator, 5 minus 5 gives us 0. X can also not equal negative 5. If we plug it in there, negative 5 plus 5 gives us 0. And if we think about this equation, this denominator over here, x plus 5 and x minus 5, it's the same two binomials as the left side of the equation. So again, 5 and negative 5, we've already identified those as restrictions. So now let's go ahead and clear our fractions. In this problem, the least common multiple that we want to multiply by are the two binomials that we see in the denominator, x minus 5 and x plus 5. That's our least common multiple. So we'll multiply both sides of the equation by those two binomials. So let's begin distributing. X minus 5, x plus 5. That cancels with our denominator, and so we're left with 3 times x plus 5, because the x minus 5 is canceled. Carry down our plus sign, and we distribute those same two binomials again. Here our x plus 5's cancel, so that leaves us with 1 times x minus 5. Carry down our equal sign. Now when we do the distribution and clear the fractions on the right side, the x plus 5's and x minus 5's cancel altogether. So we're left with just the numerator of 2. Now let's go to step 3. Let's just solve this resultant equation. We have to first distribute our expressions on the left side. 3x plus 15 plus 1x, or x minus 5, equals 2. We can combine like terms and isolate our variable. Now we can carry that on over here. Divide by 4. X equals negative 2. So let's check to make sure that's not restricted. Our actual restrictions were 5 and negative 5, so the possible solution of negative 2 works. So there we have it. That is our solution to this rational equation. And just to be clear, if we were to plug that back into our original equation, anytime where we had the value x, we would see that our equation ends up being true.